The wavelet functions. The important features of a signal can be described or parameterized not by using scaling functions and increasing the j to increase the size of the subspace spanned by the scaling functions, but by defining slightly different set of functions, wavelet functions that span the difference between the spaces spanned by various scales of the scaling functions. There are several advantages by doing the scaling functions and wavelet functions to be orthogonal. Orthogonal basis functions allows simple calculation expansion coefficients and have a Parseval theorem that allows partitioning of a signal energy in the wavelet transform domain. How the energy is going to be distributed among all the coefficients relevant to the wavelet functions and scaling functions was done by the Parseval theorem. The orthogonal complement of Vj and Vj plus 1, that means subspace of Vj and the next space Vj plus 1, the difference between these two, that means orthogonal complement is defined by Wj, that means Vj and Vj plus 1 difference will act as a Wj. Scaling functions difference is going to be spanned by the wavelet functions. This means all the members of Vj are orthogonal to all the members of Wj. Then see here, XOR gate is a generally difference gate. If two events are happening, the difference between these two events are going to be identified as an output. Similarly, here what we said, Vj space is a upper space, Vj minus 1 is the lower space, Vj minus 2 is the lower space as compared to Vj minus 1, or Vj is superset of Vj minus 1, Vj minus 1 is a superset of Vj minus 2, Vj minus 2 is a superset of Vj minus 3, Vj minus 3 is a superset of Vj minus 4. Like that, the orthogonal difference or orthogonal complement between Vj and Vj minus 1 will be noted as Wj minus 1. This is going to be notated by Vj equal to Wj minus 1 modulo 2 operation Wj minus 2 modulo 2 operation Vj minus 2. We will see this expression one more time in later. For time being, we are presenting to understand the orthogonal complement of Vj minus 1 will be needed as a Wj minus 1. We require already we said that Vj minus 1 Wj minus 1 to be orthogonal, or inner product of scaling function and wavelet function to be 0. That means orthogonal to each other. Then see here, V0 is a subset of V1 is a subset of V2, subset of up to so on L square. L square is the final set. Then already we said that V1 upper set will be defined by lower set scaling functions or space spanned by the scaling function modulo 2 operation with space spanned by the wavelet function. Then V1 equal to V0 XOR operated or modulo 2 operation with W0, which extends to V2 equal to, we can write as usual like this, V1 orthogonal, or you can say it as XOR operated with W1. Already we decided that V1 equal to V0 XOR operated W0. So in place of V1 we are substituting V0 XOR operated with W0. In general, this gives L square equal to V0 modulo 2 operation W0 modulo 2 operation W2 up to so on up to W infinite. Then V0 is the initial space spanned by the scaling function phi t minus k. V0 is the initial space spanned by the scaling function. Then pictorially we are going to show that the relation between scaling functions, space spanned by scaling functions, and space spanned by the wavelet functions. Here V3, V2, V1, V0 are the scaling functions. Here W2, W1, W0 are the wavelet functions. Then V3 is a superset of V2, is a superset of V1, is superset of V0. Initial space spanned by scaling function is given by V0. Then V1 existing, V1 is the next space spanned by scaling functions, that is a V1. just by looking into this spaces spanned by V0 and V1, there existing certain difference between V0 and V1. That means V1 is a superset, V0 is a subset. The difference or orthogonal complement between V1 and V0 is notated as W0. That is the meaning. In a similar way, W1 and W2 are defined. Here also we are mentioning one more time, W2 is orthogonal to W1, orthogonal to W0 and orthogonal to V0. Then the scale of the initial space is arbitrary and could be chosen at a high resolution of say j equal to 10 to give L square equal to V10 modulo 2 operation W10 modulo 2 operation W11 up to so on infinite. We are starting at j equal to 10. Here we are starting with lower scale resolution j equal to minus 5. Then we are moving towards the infinite. V minus 5 modulo 2 operation W minus 5. Next level will be W minus 4, W minus 3, W minus 2 up to so on infinite. Suppose you start from j equal to minus infinite, L square equal to, we are starting from minus infinite to, you are ending at infinite. So that all the wavelet coefficients are existing here, or wavelet functions spanned by wavelet functions going to be represented. Then simply by looking the previous equation, the entire expression from minus infinite to plus infinite or minus 10 to infinite or minus 5 to infinite, it is a wavelet functions are dominating, so that we can write eliminating the scaling space altogether and allowing an expansion of the form. That means we are removing the scaling space. Only we are writing in terms of wavelet space. F of t equal to summation k, summation j, ajk psi jk of t. Another way to describe the relation of V0 to the wavelet spaces is nothing as W minus infinite orthogonal, or we can say it as modulo 2 operation up to minus 1 will give you V0. That means W0 is a subset of V1. W1 is a subset of V2. Like this we can write. Since these wavelets reside in the space spanned by the next narrower scaling function, they can be represented by weighted sum of shifted scaling functions phi of 2t defined. Then psi t, as usual how we had written in a scaling function summation n h1 of n square root to phi of 2t minus n. Here h1 of n gives the coefficients relevant to wavelet functions. H of n will give you the scaling functions. The function generated by gives the prototype or mother wavelet phi t for a class of expansion functions of the form phi jk of t equal to 2 power j by 2 phi of 2 power jt minus k, where 2 power j is the scaling of a t, 2 power minus jk is the translation in t, and 2 power j by 2 maintains the L square norm of the wavelet different coefficients. Sometimes this is going to be taken as unity. Generally we are going to take it as unity. For some of the set of coefficients h1 of n, the relation between h1 of n and h of n going to be given like this. That means this is an odd symmetry, this is going to be even symmetry. For some requirement that wavelets span the difference or orthogonal complement spaces, and the orthogonality of integer translates of the wavelet are required by the orthogonality to be related to the scaling function coefficients that was given by these two equations. Simple examples. Suppose our scaling function going to be having coefficients as h of 0 equal to 1 by root 2, h1 equal to 1 by root 2. Then the function going to be appearing like this. The corresponding wavelet of our wavelet going to be looks like this. The coefficients are going to be given, and for the next reference, suppose the scaling function of a triangular function going to be given like this, then the coefficient related to the scaling function is h of 0 equal to 1 by 2 root 2, h of 1 equal to 1 by root 2, h of 2 equal to 1 by 2 root 2. Then the corresponding triangular wavelet function going to be given like this, psi of t. Then general expression along with the wavelet coefficients and the scaling functions going to be given. Already you know this at the beginning onwards, but we are referring that in terms of k. In terms of k here, because first we are defining scaling functions, later we are defining wavelet functions. Then ck equals c naught of k going to be orthogonal to this. Then djk going to be defined for different values of j. K indicates that first scaling function defined, later wavelet functions are defined. We will stop here. We will continue in the next